Welcome to Math with Professor V. In this video, we're going to learn about the Fundamental Theorem of Algebra. What does it tell us? And then what can we do with it? And at the end of the video, we're going to work through several examples based on the principles of the Fundamental Theorem of Algebra that enable us to find all of the real and imaginary zeros of a polynomial function. So first things first, what does the Fundamental Theorem of Algebra actually say? The statement is more or less the following. Every complex polynomial function of degree n greater than or equal to 1 has at least one complex zero. And this theorem was actually proven by Gauss when he was only 22 years old, and it was part of his doctoral thesis in 1799. So I remembered when my teacher told us we were going to be learning the Fundamental Theorem of Algebra, I thought, ooh, this is going to be a big day. And it is, but maybe initially the statement doesn't seem that exciting. So let me point out some key features. First of all, we have a polynomial function and it needs to be degree n greater than or equal to 1. So keep in mind that tells us it only applies just so long as we have x or whatever variable we're using for the polynomial function to the first power or higher. And we are guaranteed that this polynomial has at least one complex zero. So remember, when we say the word complex zero, that includes real and imaginary numbers, okay? So if it's real, it's considered complex. If it's imaginary, it's considered complex. If you need a little recap on what's an imaginary number, real numbers, I have a video on that, so I'll link it in the description. But this is exciting because it does guarantee us at least one solution or zero, right, for any polynomial function. So let's think back. Say you had some polynomial f of x, which equals x squared minus 9. If you were to set this equal to 0, you want to find its zeros. We could do this pretty easily. X squared would equal 9, and then we get x equals plus or minus 3. So we actually have two zeros. They're real, but that still makes them complex. And we were guaranteed a minimum of 1. Also, if you had something like g of x equals x squared plus 9, I know the zeros of that polynomial are not real. They're imaginary, plus or minus 3i, but those fall under the set of complex numbers. So then this is still satisfied. However, being guaranteed at least one is not very specific. And Gauss later went on to prove the n-root theorem, which I think is the more exciting theorem personally, not to, hate on the Fundamental Theorem of Algebra, but look at what this says. If p of x equals 0 is a polynomial equation with real or complex coefficients and positive degree n, then when multiplicity is considered, p of x equals 0 has n roots. Beautiful. So whatever the degree is of our polynomial, that's how many roots it has, as long as we consider multiplicity, meaning some roots can be repeated, right? And as long as we allow real and imaginary solutions, so we're opening it up to the set of complex numbers, your polynomial has the exact same number of roots as its degree. That's beautiful. And you probably noticed that already, right? Like quadratic equations, degree 2 equations all have two zeros. And then when you throw an x cubed in there, now there's 3 a lot of the time. Sometimes there aren't 3 real. You'll have 1 real, 2 imaginary. And when that happens, it's helpful to know what the Conjugate Pairs Theorem tells us. That's next on the docket. So lastly, let f of x be a polynomial whose coefficients are real numbers. If r equals a plus bi is a zero of f, then the conjugate, and we denote the conjugate by putting this little bar on top, the complex conjugate, a minus bi is also a zero of f. So here's the thing to remember. When a polynomial has an imaginary zero, a complex zero, a plus bi, it will always have a minus bi as a zero as well. That's why it's called the Conjugate Pairs Theorem. So a polynomial will always have an even number of complex roots. And you could think of them like they're just little penguins, right? They mate for life. A plus bi and a minus bi, they're always sticking together. You can't have one of these zeros and not have the other one. And it's also impossible for a polynomial to have only 3 complex zeros. It's always got to be 2 or 4 or 6 or 8 because these guys come in pairs, okay? So putting all of that together, we're going to now find all of the real and imaginary zeros for a polynomial function, okay? And let me just draw for you a little bit in case you don't have time to watch that other video going over real and imaginary numbers. When we talk about complex, this is the complex plane. All of the real numbers are plotted here where the x-axis normally is. Imaginary numbers are plotted vertically where the y-axis normally is. And then this whole set, these are our complex numbers. So if you have just plain old 3 plus 0i, right? No imaginary part to it. You would just come on the real axis. There's 3 plus 0i. If you have a purely imaginary number with no real part to it, say like 5i, and there's 0 real part, then you'd come up here 1, 2, 3, 4, 5, right? That's 5i. Boom. And then you can have a little mixy-matchy moment. You could have 2 plus 3i. That means the real part is 2, the imaginary part is 3. Where would you plot it? You'd go 2 in the real, up 3 imaginary, boom. There's 2 plus 3i, okay? So generally speaking, we just say these are all our complex numbers, everybody, everybody. And then if you have something with no imaginary part, then it's just real. No real part is just imaginary, mixed, 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 mixed. You can have negatives, okay? All right. Moving on, we don't need to plot them. I just want you to get an idea of what's going on. So first example, form a polynomial f of x with real coefficients having the given degree and zeros. So it tells me the polynomial is degree 3 and 2 of the zeros are given, 1 plus I and negative 8. But using the conjugate pairs theorem, I know if 1 plus I is a 0, so is 1 minus I. Very good. So how do we form a polynomial with these zeros? Well, I'm going to use the fact that if something is a 0 of a polynomial, x minus that number is a factor of the polynomial. Namely, x minus each of these zeros, 1 plus I, x minus negative 8, x plus 8, and x minus that third 0 that we squeezed out, 1 minus I, are all factors of the polynomial, okay? And you can see here, this makes sense, because if I were to set each of the factors equal to 0, using the zero product property, then I would get back 1 plus I, negative 8, and 1 minus I, right? As zeros for f of x. So in order to form this polynomial, my task now is to multiply this all out. But of course, I'm going to show you the least painful way to do it. Don't just sit there and start multiplying everything out. Whatever these two little conjugate zeros are, we're going to put them next to each other. We want to multiply those guys out first. And let me distribute the negative while I'm at it. So we've got x minus 1 minus I times x minus 1 plus I times x plus 8. Okay? And then I want you to think back. You know when you're multiplying out conjugate pairs, a minus b and a plus b, you get a difference of squares, right? A squared minus b squared. So I want you to think of x minus 1 as a, and I want you to think of I as b. Why do I want you to do that? That way you don't sit there and do this massive foiling problem, okay? So this is just going to multiply out to a squared minus b squared. This is a, this is b. So a squared would be the quantity x minus 1 squared minus b squared is I squared. Boom. And then don't forget, we still have that little x plus 8 over there, okay? I'll say that again. A minus b times a plus b is a squared minus b squared. I want you to think of all of x minus 1 as your a, and then I is b. So then I'm left with x minus 1 quantity, make sure you keep those parentheses squared, minus I squared. And then from here, it's a lot easier to multiply everything out. So we've got don't forget x squared minus 2x. You have that middle term plus 1. And then I squared is negative 1. So minus negative 1 times x plus 8. So this ends up giving us x squared minus 2x plus 2 times x plus 8. And then from there, yeah, we do have to just sit there and distribute this all out. So here's how I like to do it. This is x cubed plus this is 8x squared. And then I just start stacking underneath the next product. So that's negative 2x squared. I'm going to put it under here so my like terms are already grouped, you see? And then that's minus 16x. And then lastly, it's getting messy, I don't like it. 2x plus 16. So then I go plus 2x plus 16. And then all my like terms are stacked, so it's pretty nice. So then I have f of x equals x cubed plus 6x squared minus 14x plus 16. Okay, and then look at you. Now you could be the teacher. You could say, here's a polynomial. Give it to your little students on a worksheet and say, find the zeros. And then you already know the 3 that there are. 1 minus I, 1 plus I, and negative 8, because you made this yourself. Oh, wow, wow, wow. And I want to point out that this polynomial is degree 3, which makes sense because we were told it should be degree 3. And there were 1, 2, 3 zeros that we used in order to form it. Okay, beautiful. Now moving on, our task changes just a wee bit. Says use the given 0 to find the remaining zeros of the function. So here's f of x. It's x cubed minus 2x squared minus 11x plus 52. One of the zeros is negative 4. So what degree is this polynomial? Very good. It's degree 3. You look at the highest power on the variable. They gave me 1 0. That means I need how many more? 2 more, right? I'm missing 2. So this guy is degree 3. Now remember, if we were to factor f of x, I know since one of the zeros is negative 4, x plus 4 is a factor, right? And then I have 2 more zeros. I don't know what they are, sitting there. So f of x is equal to x cubed minus 2x squared minus 11x plus 52. Let me write that up. X cubed minus 2x squared minus 11x plus 52. If I want to know what these 2 zeros are, or these 2 factors are, what I could do is divide by x plus 4, divide my polynomial by x plus 4. These would cancel. And then the quotient here would be degree 2, and it'll either factor beautifully or I can go in and use the quadratic formula and extract them. So basically when you're given a 0, what you want to do is divide whatever factor that polynomial has based on the 0 into the original. And what's nice is, in this case, since the 0 is just negative 4, one little real 0, I don't have to do polynomial long division, I can do synthetic division. Okay, so you take the 0, which is negative 4 in this case, put it in a little square box, whatever, on the left, and then you list out the coefficients of f of x, what you're dividing into. So we'd have 1, negative 2, negative 11, and 52. You leave a blank row, okay? So leave some space here. And then the entry on the left, the far left, you always just bring it down, don't touch it. Then you multiply this entry by whatever's in the corner here. You always multiply this diagonal product, negative 4 times 1, and you write the result in the following column. So that's going to be negative 4. Then we add vertically. So this will be negative 6, and then just repeat the process. So negative 4 times negative 6, that's positive 24. Add vertically, this is going to give me positive 13. Negative 4 times 13, negative 52, and then this is 0. This is your remainder, and it better be 0 if you're dividing by something that is a factor or 0 of the polynomial. So if you don't get 0 and you used a given 0, then you messed up somewhere, okay? That's helpful. But here are the coefficients of the quotient. The quotient is always going to be 1 degree lower than whatever you were dividing into. So this guy was degree 3, my original function. This is degree 2. Degree 2. So then 1 is the coefficient of x squared. Negative 6 is the coefficient of x to the first. And then positive 13 is my constant term. So basically, my remaining 2 zeros are sitting in here, in this quotient. How can I figure out what they are? Well, I'm going to set it equal to 0. And then let's see, does it factor? No. But we don't sit there and cry because we've got the quadratic formula. So here we go. X equals opposite of b plus or minus square root b squared. Negative 6 squared is positive 36 minus 4 times 1 times 13. 4ac all over 2a. 2 times 1. So what is this going to be? 6 plus or minus square root 36 minus 52 over 2. Keep simplifying. This is 6 plus or minus square root negative 16 over 2. And then we're finding all of the zeros, so real and imaginary. So we're not stopping here just because there's a negative underneath the radical. This is going to simplify now. When there's a negative underneath the radical, the easiest thing to do is just say normally, square root of 16 is 4. So I'm just going to slap an I on there because by definition, square root of negative 1 is equal to I. So 6 plus or minus 4i over 2. That's like a really quick refresher. If you need a more in-depth video lecture on imaginary numbers, I'll link a video in the description, okay? In case you haven't seen them before. And then from here we can simplify, right? Divide the 6 by 2 and the 4 by 2. And we have 3 plus or minus 2i. So each of those are a 0. 3 plus 2i and 3 minus 2i. Okay, now the question stated find the remaining zeros. They gave me 1. These are the 2 that were remaining. Okay, they didn't ask us to write f of x in factored form, but if you were to, sometimes you're asked to do such a thing, you'd have x plus 4, x minus 3 plus 2i, and then x minus 3 minus 2i. And then there they all are. Okay, 1, 2, 3. And then again, notice, yeah, we had 2 complex zeros and they're conjugates. They always come in conjugate pairs. Cool? All right, here we go. Another one. F of x is x to the 4th minus 5x squared minus 36. And one of the given zeros is negative 2i. So right off the bat, if negative 2i is a 0, that's like 0 minus 2i. Then 0 plus 2i, right, is also going to be a 0 of this polynomial. So I've got 2. How many more do I need? Well, this polynomial here is degree 4, so I'm missing 2. I need 2 more. So think about it this way. F of x factors into x plus 2i, x minus 2i, and then x minus something, right? And all of that is x to the 4th minus 5x squared minus 36. So just like last time, I want to divide the original polynomial by both x plus 2i and x minus 2i. X plus 2i, x minus 2i. That way, the quotient, what's left over, will contain the remaining 2 zeros. Okay. Now, last time we used synthetic division, and you can use synthetic division with these complex zeros, but it gets really messy. I remember my high school teacher told me you couldn't, and I was like, I'm gonna try. And I did it, and it works, but the better thing to do is to multiply these out, believe it or not, and then just do long division and divide it into the original. Now, if you're noticing a faster way of doing this, I see it too, don't worry. I'll show you guys that at the end in case anyone didn't notice. But let's just go through the same process as we did for the last problem first, and then we can talk about that, okay? So in this case, I'm gonna multiply these out first, and then long divide, okay, into f of x. So x plus 2i times x minus 2i, that's actually not bad to multiply out because they're conjugate pairs, right? So that's going to be x squared minus 4i squared. And then remember, I squared is negative 1. So then this becomes x squared plus 4. So we're going to divide that, that's our divisor, into the OG polynomial f of x, which is x to the 4th. Technically, I should be putting placeholders, but I don't really need them. Minus 5x squared minus 36. Okay, so when you're doing long division, just look at the leading terms. What do we multiply x squared by to make it x to the 4th? Another x squared, right? And then you take that x squared, distribute it out here. So that'll be x to the 4th plus 4x squared. So when you distribute, you write the result underneath, and then you subtract that from the row up above. This entry on the far left should cancel out. And then negative 5x squared minus 4x squared is negative 9x squared. Then we bring down the negative 36. And don't worry, I have videos going over polynomial long division in case you forgot. Okay, then you repeat the process till you can't anymore. Meaning, what do you multiply x squared by to make it negative 9x squared? Negative 9, right? Then you distribute, you multiply that out by the divisor. You write the result in the row down here. So this is going to be negative 9x squared minus 36. Subtract this from the row up above, 0. And you should get remainder 0 because we're dividing by a polynomial that contains zeros of the original. So it better go in evenly, otherwise we messed up. Okay. No, this is exciting because here's my quotient. Here's my quotient. So my remaining two zeros are sitting in here. So we set x squared minus 9 equal to 0, which means x squared equals 9. So x is plus or minus 3. So the problem asked me to find the remaining zeros. Technically, one of them was 2i, and then the other two plus or minus 3. So the remaining ones are 2i, 3, negative 3. And if we were to write f of x in factored form, we'd have x plus 2i, x minus 2i, x plus 3, and x minus 3. Okay? Now, I did say there was a shortcut. And the shortcut won't work on every single polynomial, but when it does work out, it's very nice. So in this case, f of x, which is x to the 4th minus 5x squared minus 36. Even if they hadn't given me any zeros, if you notice that this factors into x squared minus 9 and x squared plus 4, then you're pretty much on your way, because then x squared minus 9 we can factor into x plus 3, x minus 3. And then x squared plus 4, you could just set that equal to 0. If you were totally starting from scratch, x squared equals negative 4, so x is plus or minus 2i. So x plus 2i, x minus 2i. But like I said, not every single polynomial that you're given can you spot how to factor it right off the bat this nicely. So the method that I did first, even though it's longer, will always work. Okay? Very good. I have just two more. I like these better than when you have to do the rational roots theorem and just kind of guess around, because at least this one you're on the right path always. Okay, here's our polynomial f of x, which is x cubed minus, or plus 4x squared, excuse me, minus 10x plus 12. And one of the zeros that they gave me is 1 plus I. So how many are there going to be total? 3, right? Very good. And that means I'm missing 2. Right off the bat, I know what else is a 0. 1 minus I. Very good. So what we're going to do is make a polynomial, x minus 1 plus I, x minus 1 minus I, multiply that out, and then divide it into the original, just like we did last time, okay? I'm not going to write out all of the reasoning why, because we've done it a few times now. So after we multiply this all out, right, these are two factors of this original polynomial. If I divide them into it, the quotient will contain my one missing zero. Now remember, I showed you a slick way to multiply this out. Did you remember it? Distribute the negative, yeah. X minus 1 minus I, x minus 1 plus I, and then remember, you treat x minus 1 as A, and then you treat I as B. And so you basically have A minus B, A plus B, and that gives you A squared minus B squared. Remember, we just did that like a few minutes ago. Yeah, okay. So we're going to have x minus 1 squared minus b squared, which is I squared. And then multiply x minus 1 squared out. If you need to write it twice and FOIL it, that's fine. But I think it's easier if you just memorize the pattern. It'll be x squared minus 2x plus 1. And then minus I squared, that's minus negative 1. So that's going to be plus 1. So this is x squared minus 2x plus 2. Okay, so now I'm going to take this guy, long divide it into the original. So x squared minus 2x plus 2, divide this into x cubed plus 4x squared minus 10x plus 12. Here we go. So what do you have to multiply x squared by to make it x cubed? Just x, right? Very good. Then distribute. Write the result underneath. So x cubed minus 2x squared plus 2x. Then subtract that from the row up above. So this goes bye-bye. It better. Just don't forget there's a minus here, okay? That's a tricky part. A lot of students forget. So if you think that might be something you're going to forget, I would distribute it and switch all the signs here. It makes it look messy, so I don't like to do it, but if you think you're like a forgetful with those negatives, then take that precaution. Okay, so we've got 4 minus negative 2, that's positive 6x squared, negative 10 minus 2, so negative 12x, and then bring this guy down. Good, you got it? Okay, beautiful. And then the question is, what do I multiply x squared by to make it 6x squared? 6, so that goes up top, positive 6. Again, distribute. Write it underneath. 6x squared minus 12x plus 12. And boom, remainder 0. Now you guys, what if I didn't have remainder 0? What would that tell me? I messed up, exactly. So go back, check. Probably you screwed up somewhere here, or you might have screwed up making the polynomial. It should be remainder 0 if you're dividing by a polynomial that was formed using zeros of the original polynomial, okay? But here we go. X plus 6 is the quotient. So my one remaining 0 is sitting right in there. I'm going to take x plus 6, set it equal to 0, and I get x equals negative 6. So the remaining zeros, they only gave me 1 plus I. I went ahead and found 1 minus I and negative 6 with your help. No, it wasn't all me. And then they didn't ask, but let's just write f of x in factored form. Let's just show off how good we are. X plus 6, x minus 1 plus I, x minus 1 minus I. Okay, beautiful. Why did it make it an arrow? I still don't understand. Okay, I've got one more for you, and it's super similar to this one. So you know what I think you can do? I think you can pause the video and try it on your own. I really do. Don't be scared. Just give it a go. If you get stuck, guess what happens? You hit play, and then I finish it with you, okay? But just try. See if you've got a hang of what's going on. Okay, did you try it on your own? I hope you did. This one is the grand finale. This is degree 4, so there should be 4 zeros total. One of the zeros is 3 plus 2i, so I'm missing 3. but I know right off the bat 3 minus 2i is another 0. So again, I'm going to make a polynomial that contains these two zeros and then long divide it into the original. So x minus 3 plus 2i and x minus 3 minus 2i. I know those are zeros of f. And let's multiply this out. We're going to use that little slick trick again. So x minus 3 minus 2i, distribute the negative. And then now I want you to think of x minus 3 as your a, and then 2i is b. Okay? So then you're going to have a squared minus b squared. So x minus 3 quantity squared minus 2i quantity squared. Did you get up to there okay? If you made it this far, be proud of yourself. High five. Okay. Now be careful. X minus 3 quantity squared, when you multiply that out, it's going to be x squared minus 6x. You keep the sign the same. You multiply these guys by each other and double it. That's the shortcut. Plus 9. Always square the last one. And then minus 4i squared. Did you remember to square the 2 as well? It becomes a 4. And then I squared is negative 1. So really all of this is just positive 4. So now we have x squared minus 6x plus 13. If I take 9 plus 4. How you doing? Okay, once we have this little polynomial, degree 2, that contains these two zeros, now we long divide it into the original. All right. X squared minus 6x plus 13. Divide it into 3x to the 4th minus 22x cubed plus 64x squared minus 58x plus 13. Okay, don't get overwhelmed. Just pay attention to the leading terms. Nobody else matters. What do you multiply x squared by to make it 3x to the 4th? 3x squared. Very good. Distribute, distribute, distribute. Write it underneath. So it'll be 3x to the 4th minus 18x cubed plus 39x squared. Then I subtract that from the row above. Don't forget the negative distributes with it. This cancels. Now this is negative 22 plus 18, so that's going to be negative 4x cubed. And then 64 minus 39 is plus 25x squared. We okay? Then bring down negative 58x, and then repeat the process. And don't get overwhelmed. Just look at the leading terms. What do you multiply x squared by to make it negative 4x cubed? Negative 4x. And then that distribute, distribute, distribute. So it'll be negative 4x cubed plus 24x squared minus 52x. Subtract from above. This cancels it better. Then don't forget to distribute the negative. So 25 minus 24 is just 1x squared. Negative 58 plus 52 is negative 6x. And then bring down the 13. Oh, look at that. Beautiful. And then what do you multiply x squared by to make it x squared? Just 1. And then, I mean, we don't have to finish this step, but why not? Just so we get the satisfaction of going, boom, here's my remainder 0. And again, if it wasn't 0, what does that mean? We messed up somewhere. Either we messed up in the division or you don't have the right polynomial out here. You didn't multiply correctly. Okay, we're almost there, you guys. Yay. So the remaining two zeros are sitting right in here. They're hiding from us. So we're going to say, come out, come out. 3x squared minus 4x plus 1. I'm going to set u equal to 0 and get the remaining zeros out. Do we need the quadratic formula? No, this factors. 3x minus 1, x minus 1. Boom. Yes, I love it. Then you set each of these factors equal to 0. You could probably do it in your head, huh? That's so fancy of you. Okay, so then you get x equals 1/3 and x equals 1. So all of my zeros, we got them. The missing ones were 1/3, 1, and 3 minus 2i, because they gave me 3 plus 2i. That's all they gave me. Should we write it in factored form? I mean, why not? So here's two of the factors. So f of x is 3x minus 1, x minus 1, x minus 3 minus 2i, x minus 3 plus 2i. That's one way to write it. Another way, if you actually wanted to write it with 1/3 and 1, okay, let me show you what you have to do. So if you have x minus 1/3, x minus 1, and then the other ones are the same. Here's the issue. Are you ready for the issue? If you were to sit there and multiply this out, the leading term would be x to the 4th. But look at your original polynomial. What was the leading term? It was 3x to the 4th. Where'd that 3 go? Well, we lost it. We lost it at this step. When we moved the 1 over and divided by 3, it went away. We divided by that constant. So you got to bring it back. You got to say, oh, well, there's a 3 in the front. How would you know to do that? Well, you just look back at your original, right? And then also, since there's a 1/3 here, basically you need this 3 so that when I distribute back through, it cancels and there's no fractions. Because look at the original polynomial. All of these were integer coefficients, right? So you shouldn't have like a 1/3 as a factor, because otherwise if you sat there and multiplied this all out without the 3, you'd have a bunch of fractions in the polynomial, and that doesn't match what it was originally, okay? So two ways to remind yourself. One, if you look here, these are all 1x's, 1x's, 1x's. The original had a 3. Or if you notice there's a fraction and there were no fractions in the original, just whatever the denominator is, it should be out there. So it cancels. That was probably more than you needed, but I like to be thorough. You know what I mean? So that concludes the video. Give it a thumbs up if you found it helpful. Subscribe if you haven't already. And like I said, if there were some topics that I went over that you feel like you're a little rusty on, then check out the description, because I've linked a lot of the videos going over imaginary numbers, long division, and I also have full-length video lectures organized into playlists for algebra, pre-calc, trig, calc 1, 2, 3, pretty much everything you could possibly need if you're starting out in math in college or high school. And follow me on Instagram, TikTok, Math with Professor V. I'll be back sooner than later, guys. Bye.